right, live on YouTube.
Woo woo.
Live on TikTok. Okay.
We'll do it live.
We are live.
Ah.
I didn't mind everything downstairs.
Bye. MATHursday.
We're close.
Closed is fine. All right, welcome to MATHursday. Let's go ahead and get started. Here's a little radical for you to simplify. All right, so when you know it, put it in the chat. And we'll get into it. I'm just going to clean up my board. Okay, so we got a little radical there for you to simplify. When you think you know the answer, go ahead and put it into the chat. And welcome to MATHursday. It's a little bit hard to read, huh? So it might be a little bit easier. That's a little bit easier to read, huh? All right, guys, so we've got a little radical for you to simplify right here. Already got some guesses, or not guesses, but some answers in the chat. Ooh, calculating square root by hand. You know, it's not really often that you need a rounded number. Usually when you're working with square roots, at least in the more kind of advanced maths, you're really going to be this is a more exact answer than like if you rounded it to like, what would it be? It would be 6 point something, right? All right, so I see a lot of people joining in. Welcome to MATHursday. So this is just where we get into all things math. I've been a math and science teacher for over 20 years, so I'm here to help. So this is, we mainly focus on pre-algebra through like algebra 2, pre-calc, trig a little bit. But mainly it's just going to be a lot of algebra 1 and a lot of algebra 2 that we get into. But if you have any questions or you've got a quiz coming up or a test coming up or a midterm, it's getting to be midterm season, pop it in the chat and we'll see what we can do. Okay, so I see a lot of people kind of going between like, is it 6 point something or this 3 radical 5? Okay, so when we're simplifying these radicals, like yes, I could put this into a calculator and I'd get 6 point something or other, but that's going to be a rounded answer. So in this case, what we do is we would simplify this, right? And when we're simplifying a root like this, we want to break it up and think about any factors that are perfect squares. Okay, so 45, we think about the factors of 45. right? So we can have, I mean, obviously 1 and 45, 2, no, 3 and 15, yep. 4, 5, and 9, and that's it. So here, this 9 here is a perfect square, okay? So what we do is we look at 45 when we rewrite this as 9 times 5, which is just substitution, right? But it's still under the radical sign. I've got 9 times 5. So I can take the square root of 9, which is 3. But I can't take the square root of 5, so that 5 can't come out from under the radical symbol. So it stays like that. So simplifying it down is 3 root 5. Okay, so that's for simplifying radicals. It's sort of like, you know, with like 4/8, right? You could write 4/8 as, we wouldn't leave it as 4/8, right? We would write it as 1/2. And there's some other things when you're working with radicals like this, when you work with like polynomial functions and quadratic equations and things like that, where you do need the exact answer. And this is the exact answer, not that 6 point whatever. Okay, so let's do another one. Let's try another one. Let's put another one up on the board. Let's see, we had square root 45. Let's do root, let's do root 32. Okay, so square root of 32. Let's look at that one. Samsung, finding the pole of a complex function. That's probably a little bit further, a little bit out of the realm of the scope of what we focus on here. We pretty much stop kind of at algebra 2 or pre-calculus. But if you have something more specific than that, then put it in the chat and you might be able to, somebody might be able to help you out in this. So right now, we've got this one here. So we're gonna simplify this root. Okay, so we've got square root of 32. Oh, good. I love it when we're doing people's favorite subjects. All right, so I see a lot of 4 root 2. Okay, so again, so yes, King. Yes, it's, oh, sorry, not King. Roger. It is going to be 5 point something if we were to round it, but in this case, we're going to just simplify it. We're not going to round it. So 32, remember, we want to break it up into our perfect squares. So we think about what is 32 divisible by, or you can do a factor tree, prime factorization, all of that. And you figure out that 32, the perfect square is 16 times 2. Okay, so we can take the square root of 16, which is 4. But we can't take the square root of 2, so that stays as root 2. And that is our simplified radical. Okay. So again, we're just simplifying these. Okay, we're just simplifying these. It would be 5 point something, but we would just simplify them, okay? All right. So welcome to Math Thursday. Those of you who are just joining us, maybe this is your first time, maybe you're a long-time listener, I don't know. But you want to, so go ahead, and if you have any questions or any problems that you're having in math, or you want to go over anything or learn a concept, or maybe you have a test coming up or something like that, pop it in the chat. We typically go through like pre-algebra through algebra 2 is where we kind of stick around. So we're not going to get into the chain rule And DMA for logarithms, I can do kind of basic logarithms, but it kind of depends on what you're learning about with the logarithms. Yeah, Damien, I definitely do trig. Okay, so Trent, let's see, can you do exponents under a square root sign? Yeah. So when we're looking at a radical like this, and there were a couple of questions up above about how we figured out that it was 16 times 2. And really, I mean, 32 is one of those highly divisible numbers. So what I usually do is I can do like 4 and 8. 4 is a perfect square, but 8 also still has a 4 in it. So that kind of prompts me to keep looking. So then I see that 16 is a really big perfect square in there, right? So it's a really big perfect square in there, so I can take that one out. Okay, so if I have a root like this, okay, but if there were some sort of exponent under there, like with a variable. Okay, so if there's a variable under there with an exponent, that's okay. We still do this. It's still the same idea. Okay, so if we look at something like, let's just stick with 32. Let's stick with 32 because we already simplified that one. And then x squared y. Okay, so 32, we kind of already went over with like how we simplify that, right? But so when we're looking at these, we're going to look at each thing and can we simplify the square root of that? So the square root of 32, we already kind of established. So this is 16 times 2. So that 16 can come out and it becomes 4. But that 2 is going to stay behind, right? So let me see. I'm going to do that. Then I have the square root of x squared. And then I have the square root of y. So what I can do is if they're all under the same radical sign, I can just sort of split it up into these multiplication things, okay? So square root of 16 times 2, that's going to become 4 root 2. Square root of x squared is a perfect square, so I can take the square root of it. The square root of x squared is just x. And then the square root of y, I can't take the square root of that because I don't know what it is, so it's just the square root of y. So now I can combine them all back together. I can put everything that's under a radical sign underneath the same radical sign, and anything that's being multiplied goes out first. So this would become 4x root 2y. Okay, because the 2 can't come out and that 1y can't come out. So that's how you would simplify this with if you have exponents and variables underneath. Okay. All right, so I see, let me see. Okay, so Kevin, parallel lines and transversals. Dividing, yeah, we can keep doing the dividing functions. How do I get 4 to, oh, how do I get this 4 root 2? Because I can take that, so 32 is the same thing as 16 times 2. 16 is a perfect square, okay? So the x doesn't have the square roots because I took the square root of x squared. So the square root of anything squared is just that thing by itself, okay? All right, can you do dividing radicals with rationalizing? Yes. Okay, so, man, tonight is gonna be a radical night. Okay, so if I have something like, Okay, actually, here's what I'm going to do. I'm going to start out with the square root basically of a function. Okay, over 3. Okay, so when you have the square root of like a fraction like this, this is the same thing as taking the square root of the numerator and the square root of the denominator. Okay, ooh, that's kind of hard to read. So it's the same thing as square root 32 over the square root of 3. And it's a bit easier. So we've got square root 32 over square root of 3. So now I know we keep working with square root of 32, but square root of 32 is 16 times 2. So I can take the square root of 16 and that becomes 4. But I can't take the square root of 2, so that stays as 2. Okay, so again, here's a breakdown of how I get from square root 32 to 4 root 2. Okay, so 32 is 16 times 2. I can take the square root of 16, it becomes 4. And I've got the square root of 2, it can't come out, so it's just going to stay under root 2. Over root 3. Okay. Now, one thing that math teachers will ask you to do is rationalize the denominator. Why times 2? Because I can't just say 16 because it's 16 times 2. So that's why it's the 16 times 2. So here we've got 4 root 2 because I can take the square root of 16 and it's 4. But I can't take the square root of 2, so it stays underneath the radical sign with the 2. Okay. All right. So this radical being in the denominator is kind of a big no-no in math classes. So you have to do what's called rationalize the denominator. So if I look at this, so let me see. So 4 root 2 over root 3. I don't want that radical in the bottom. So what I can do, is I can multiply by root 3 over 3 because I can always multiply things by 1 and they're still going to be themselves, right? That's just the property of the multiplicative property of equality is I can multiply by 1. But in this case, I'm going to multiply by a version of 1 that helps get rid of that radical. Okay. So I'm going to multiply by root 3 over root 3. So root 3 times root 3 becomes root 9, which is just 3. Because the square root of 3, think about this, like the square root of 16 times the square root of 16 would be 4 times 4, which is 16. So the square root of 3 times the square root of 3 becomes 3. 4 root 2 times root 3 becomes 4 root 6. They're both under the same radical, okay, under the same square root. So I can stick them together and I can multiply them together. Okay, so this is going to be 4 root 6 over 3. Okay, now, if I were working through this, and if I noticed that, like, if this were like 4 over 2, right, I would simplify that down just like a fraction, right? I can't do anything. I can't really simplify this radical unless I were kind of doing something like this up here, right? But with this, this would be my final answer. Okay, this is where I've simplified the radicals and I've rationalized the denominator. Okay. So Timmy, this is a great question. So the rationalizing the denominator, the only reason I make my students do it, like, you don't actually have to do it. It's fine to leave. That was the dog. It's fine to leave the radical in the denominator, okay? it wasn't fine before we had really powerful calculators and things like that that can work with this, right? Sometimes you want to keep it, absolutely. So the only reason that I make my students rationalize the denominator is so they can recognize that like these are the same thing when it's on an answer key, because all of the answer keys and all of the textbooks are still making students rationalize the denominator. That is honestly like pretty much the only reason that I ask them to do it, but also like SAT, ACT, those standardized tests, they're gonna give you a rationalize the denominator. So if my students are looking at this, right, they get this as the answer, which I say is great, it's totally fine, they're not gonna realize that this is the same thing. So that's the only real reason why you kind of have to do it, and some teachers still require it, again, because of all those reasons that I just said, okay? I can't simplify the 4 and the 6 because this isn't just 6, this is square root of 6, okay? Let's see. Yeah, so this is gonna be a lot of what you come across in trig when you're solving quadratics, things like that, when you're dealing with like the irrational solutions. Okay, so how do you know when you can simplify the number? You mean like underneath the radical? You look at the factors. So you look at all the factors that they have and you're looking for perfect squares like 4, 9, 16, 25, right? All of those perfect squares, if that's any of those factors, you can simplify it, okay? Hi, Mac. So Ava, I can do logs, but can you explain a little bit more about like what you're looking for with the logs, right? So I can do some like simple logs, kind of like what is a logarithm and things like that. But let's see. So Andrew, we don't really get into calculus with this. We don't really get into calculus here. We usually stop at about algebra 2, a little bit of pre-calc, and some trig stuff. So why is the 4 outside of the squared, the root 2? So the reason the 4 is outside is because of this, that 32 is 16 times 2, and I can take the square root of 16. So the only way that a number can come out from underneath the square root or the radical sign is if it is a perfect square. So 16 is a perfect square, it can come out and it's 4, but 2 is not a perfect square, so it has to stay. Okay. All right. Angelica, we don't really get into calculus here. Man, there's a lot of calculus questions tonight. But if you have a specific question, you can put it in the chat, and there might be some people, there's a really good community here. People help each other out all the time. Okay, so piecewise functions. Yeah, Maria, I think is your name. Algebra 1 help? Yeah, put it in the chat. Give me an idea of what it is. Okay. Let's see. Okay, Bryce, you got to be a little more specific about linear equations, because linear equations is a whole bunch of stuff. Okay. MP, you should start a calculus stream. That'd be great. Because it's really hard for me to get into calculus on here with these types of things, right? Okay, so let's see. Okay, hold on. Oh, the chat's going really fast. It's hard for me to see. Solving logs that involve fractions. Yeah, so I'm gonna do piecewise functions in just a second, okay? All right, so Bryce, give me a little more specifics about linear equations and things like that, okay? All right. Yeah, let me see. Hold on. Who was it? Oh, Timmy. Yeah, Calc 2. I know. You forget. You go back and you're like, oh, it's so cute that you guys are doing when you're in Calc 2 and Calc 3. Oh my God. They are, woof. Okay. Oh my gosh. This chat is going crazy. The hardest part of calc is actually the algebra. There's a lot of stuff that you just forget about, right? Okay, so Sophie, we're gonna do piecewise functions. Okay, so a piecewise function is a function that is split up into pieces. That's why it's called piecewise functions. I say it all the time. Mathematicians are not super creative at naming things. It's either like very specific about what it's talking about, right? Or it's after somebody's name, right? That's sort of the two options of naming a theorem or a process or whatever, right? So piecewise functions are just functions that are split into pieces, okay? So, that's from another session. Okay. So a piecewise function might look something like this. So it'll be something from here to here. It's this. And then from here to here, it's this. And then from here to the rest of the way, it's like that. Okay, so this is still a function, right? It still passes the vertical line test. Okay, these are really fun, actually. Once you kind of get what they are and you realize like, oh, it's just a function that's split up into pieces, right? It's going to be, they can be really fun, and you can make some really cool images and pictures and things with them, okay? Okay, so Maria, the vertical line test means if you have a vertical line and you pass it over, if it only passes through the line in one place, that means that it is a function. Okay, that's the vertical line test. So I know that these kind of overlap and these overlap, but if you notice, this one is filled in and this one is open. This one is filled in and this one is open. Okay, so these are piecewise functions, and once you learn them, you usually start by just learning them with just linear, maybe a quadratic or something fit in there, okay? But what we're looking at is you've got these ranges, right? So it would look something like when if x is greater than or equal to, what is this, 2, 4, 6, 8, 10, 12, to negative 12. Oh my gosh, one of my boards is broken. Oh no. So if x is greater than or equal to negative 12 and less than 1, 2, 3, negative 4, okay, then my equation is f of x equals negative 3. Okay, so that is this line right here. That's this little segment here. Okay, so you would say when x is between negative 12 and negative 4, f of x is negative 3. That's that line, right? F of x is negative 3, or y equals negative 3. Okay. So then here, let's see. So when x is between, this is negative 4 and positive 1, right? I'm going to write this in a different color just to kind of keep track of this. Okay. So this one here, when x, so negative 4 is less than or equal to x, which is less than or equal to 1, right? So from here to here, it's going to follow this line. Okay, it's going to follow this line, which, let's see, it goes from negative 4, it goes from 0 to 7. So the slope is 7. Oh, why did I make it? No, sorry, the slope is not 7. The y-intercept is 7. It's 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. So the slope is, that's not going to be right. Ugh. Yeah, we're just going to go with it. Let's just say, so the slope is 7 over 5x plus 6. I know that's not exactly what it is, but we're just going to go with it for now. Okay? Yeah, it's that is like a perfect thing. Like, I understand it, but I also don't, right? It's much more, it's simple, right? It is simple, but remember, I say it all the time. Simple doesn't mean it's easy, right? Simple doesn't mean that it's easy. That 6 is just what that y-intercept is. So this is the equation for this line, okay? So what it's saying is the piecewise function, it's this function that kind of follows here, follows here, follows here. Okay, now somebody asked in there, like, when am I ever gonna use this? In your day-to-day life, you're probably never gonna use it, but you can use it. It can be used for different, like, finding like quadratic, like lines of regression, like lines of best fit, different functions, things like that. But it's also just looking for patterns, right? Seeing patterns and seeing that these things are different, okay? Okay, arithmetic progressions, we're probably not gonna get into that. SAS, SSS, SSA, and thing, please. Dill, is that, are you talking about congruence or similarity or proofs? Oh, discriminants, quadratic formula. Yep, we can do discriminants. Let's see. All right. Not VODs. This is called piecewise functions. Okay. Yeah, get it. Later's the bookworm. Yep, got it. Taxes would be useful. I agree. Okay. So let's see. What was I just saying? Oh yeah, Dill, as the SAS and all of that stuff. Piecewise can't be rough. It can be rough, yeah. So Dill, it's really hard for me to show you how to fully like write a proof. But what I can do is with the SAS and SSA and all of that, I can walk you through kind of how, like, sort of the logical reasoning that you would use behind it. Let's see, let me find a good example. Okay, here we go. All right, this is a good one. Okay, so we've got this little like bow tie kind of diagram. This is one that you see a lot on standardized tests, is this type of diagram. Okay, so we'll call this B, E, C, D, and A. Let's say these two angles are congruent. Okay, so here we've got this diagram. Okay. So here's the diagram. So this is all the information that we're given, and what we're going to be asked to do is prove ABE is congruent to DBC. Okay, so we're going to prove that triangle ABE is congruent to triangle DBC. Okay, so now I'm not going to write out the whole sequence and all that, because those are really hard to do in this format, right? It's hard to do because it's going to be hard for you guys to see it and blah, blah, blah. Okay, so proving that the triangles are congruent. So this is where we get into like can we use, like, do we know 3 sides, or can we figure out that 3 sides, right? Do we know like the, side angle side? Well, we have these 2 sides are congruent. We have this angle across. So the only way that we would be able to do, when we're looking at this, we want to look at, okay, what do we know for sure, right? With your proof, what do we know for sure? Okay. What I do know for sure, beyond the information that I'm just given, is that this angle here is congruent to this angle here because they are vertical angles. I know that's always true. Okay, so in my proof, I would outline like angle ABE is congruent to angle CBD because they're vertical angles. Once I have that, now I have an angle, and a side. And if an angle, side are congruent in the 2 triangles are congruent. Okay, so I can use angle, side here. So it's a question of, use what you're given and then use that to figure out what you're going to do, how you're going to actually prove that those 2 triangles are congruent, right? So kind of figure out, like, what do I know? What can I figure out? And how is that going to get me to my proof? Okay. Yep. So proving right triangles are congruent are using HL, right? Hypotenuse leg, if you're given that information, right? But this is kind of what the overall things are for these proofs, right? Let's see. So these are all kind of the same. Let's see. I don't want to do that one. Okay, there was another one that I was working on with a student the other night. It was pretty, whoops. Let's see. Okay, let's see. I like to have. Okay. Oh, okay. Here's one. That's a good one. Oh, I shouldn't have erased that. Oh, well. Okay. All right. So here, there, there. Okay. Okay, so you're going to try to prove that triangle ACD is congruent to triangle ABD. Oh, I kind of drew it a little crooked. Whoopsie. All right, so it's a right triangle. Hypotenuse leg, we don't know the hypotenuse, right? But we do know this leg, right? So the only information that we're given are that these 2 angles are congruent and this angle is congruent. Or so you would think, right? So what you could also do, so again, this is just kind of walking through you, right? Now, there are different ways to prove different things, okay? There are different ways, there are different ways to prove the same thing, okay? So looking at this, right, I know that this leg is going to be the same for both of these triangles, right? So I've got angle, side here. Now, how else could I prove that, right? I could also prove that by kind of like looking at this and saying, okay, well, this angle and this angle and this angle would all equal 180, right? They would add up to 180, or you could say this angle and this angle are going to add up to 90. And then you could prove that, and then what that proves is that these 2 angles are congruent, okay? So then you can say angle side, because you know this side is going to be equal to itself. That's that silly reflexive property, right? But now you've got angle side angle. So that's two different ways to solve the same, or to prove the same thing, right? So the thing that it doesn't tell me is I don't know that that AB and CA are congruent. I don't know if that's congruent, okay? So you would have to kind of look at a different way. Now, once I prove that they are congruent triangles, then I can use the CPCTC to say that CA equals AB, or that CD equals DB, okay? So if you're given that information, then you can prove that and all of that, okay? So ASA and AAS. Okay, that's a great question. So when we started out, I said you could prove this using angle side, right? Using AAS. So AAS is angle side. Okay, that means you go from an angle to the side that's congruent. Okay, and it could be side angle, that's fine. Okay, angle side angle is where we look at, it's all, the reason why they're in that order is because that's the order that they're in. I know that sounds really stupid, but the reason they're in that order is because that's the order that you would come across them. So here I could have angle side angle. So when I kind of go around the triangle, that's the order that I'm going to pass through them, right? So angle side angle, or angle side. That's two ways to prove the same thing. Okay, so you don't necessarily have to use the hypotenuse leg when it's a right triangle. Okay. The order, do you do it based off of the triangle name when determining the theorem? So you don't necessarily do it off the triangle name. So this is based on the name, right? It's based on the location, that ACD, A is the 90-degree angle, C is the one swoop, D is the two swoops, right? So that's why this is ACD is congruent to ABD, because it's 90 degrees, one swoop, two swoops. But yeah, but I think you're talking about the AAS or the ASA. It's all the order of what you have or what you can prove. So what it's saying is, like, when it's ASA, it's saying if those are congruent between two triangles in that order, they are congruent triangles. So if I just know angle, side, angle, I know that these two sides are also congruent, these two sides are also congruent, and this angle is congruent, okay? So that's what we kind of look at, okay? All right, okay. Well, Dr. Carmen, I mean, nobody's forcing you to stay here, so if you don't want to listen to me talk, you can go. Okay, let's see. Arithmetic progressions. I know you've been asking that a lot. Are you talking about, I'm not sure what you're talking about. Okay, so Caleb is function. Maria, I'm live at this time every Thursday, so it's 8:45 my time now. But yeah, I start at 8 o'clock. Okay. All right. So Caleb will do the function notation and then polynomial end behavior. So Axel, yeah. So let me do polynomial end behaviors. Okay. I'm going to write out my list, polynomial end behaviors. And then there was and then function notation. Yeah. So Caleb, I'm going to do function notation right now. because that's helpful when we start talking about polynomials and behaviors and all of that. Okay. Okay, so arithmetic progressions. I've talked to you about it a couple of times, but I'm not sure what you're asking for. So you've got to be a little bit more specific. Like, give me a specific question on that. Okay. All right. Yes, that's true. Angle A is congruent because right angles are congruent. Yep. Okay. All right, so function notation. All right, so function notation is something that you'll start seeing probably hopefully in pre-algebra, but sometimes some teachers don't teach it until Algebra 1 or even Algebra 2. But function notation, when you've got something like this, okay? Ultimately, this f of x is really the same thing as y, right? When we graph it, right, we use the y-axis and we use the x-axis. But it's a function. So as I said earlier, right, we've got the vertical line test to see what it is, right, that it's a function. So if I've got f of x equals 2x plus 1, this x right here, this x is my input. Okay, so it's whatever I put in here, and then what I get out is my f of x, is my f of whatever it is, okay? So whatever I have in my input, that's what's gonna go there, and it's gonna go times 2 plus 1, times 2 plus 1, times 2 plus 1, okay? So f of, I'm gonna do some color changes. F of -3, let's say, okay? Well, actually, I'm going to erase this first. We'll do -3, but I'm going to actually set this up first. Equals 2 times whatever's there plus 1. So function notation, if you think about it like this, right? F of whatever's here is 2 times whatever was there plus 1. So if I put in a -3, it's going to be 2 times -3 plus 1. So f of -3, 2 times -3 is -6, plus 1 is -5. If I put in f of 4, it's going to be 2 times 4 plus 1. So f of 4, 2 times 4, which is 8, plus 1 is 9. Okay, that's all it is. Again, simple. They can get more complicated, right? But it's pretty simple. Whatever's in the parentheses, it can even be another variable, right? So then f of a would be 2a plus 1. It could be a whole expression, right? It could be like f of x plus 1 equals 2 times x plus 1 plus 1, and then you would simplify it, okay? But it's the exact same process. No matter how complex this gets, it could be some crazy bonkers like polynomial function. The input is the input, and then you simplify. That's it, okay? Simple, not always easy, okay? So this is a little more, this is when you're getting a little bit more into Algebra 2, but you can, sometimes some teachers will start showing this a lot earlier. Oh, Ken's, you're about 45 minutes late for simplifying radicals. So if you go over to YouTube and rewind to the beginning, I did a whole thing on simplifying radicals, see? Okay, all right. So why did that do that weird little hat thing? That's weird. Okay. Oh, polynomial and behavior. Okay. Polynomial and behavior. So polynomial and behavior is, again, pretty simple, but it can be a little bit confusing. Okay. So the end behavior is talking about where it's going to end up. So a polynomial, the end behavior for a polynomial, again, is where you kind of go like polynomial functions and polynomial equations are ultimately sort of like a not sort of like a, but they are a quadratic. So a quadratic is a polynomial. Okay, hold on just a minute, guys. Sorry. Okay. I don't know what's happening. Hold on. Okay. So what you've got is you've got a couple of different options, right? Your polynomial, if you have a parabola, right? It could open down like that. It could open up like this, right? So the end behavior of these is that they're going to be the same, okay? No, we're not going to do calculus differentiation. We don't really get into calculus on here because it's really hard to show on here. And yeah. Thanks, Cole. All right, so this polynomial, this is a quadratic, okay, because it's just a basic parabola. The end behavior is that here, the end behavior, they're both going in the same direction, okay? So as x increases and as it decreases, the y value is going to be going towards negative infinity. So they're both going to be pointing down, okay? So this is where your leading coefficient is negative and you have an even number. Okay, your even, your degrees, right? Your highest degree is even. Okay, so if it's an even polynomial, they're going to be going the same direction. If the leading coefficient is positive, they're going to be pointing up. If it's negative, they're going to be pointing down. Okay, that goes for any polynomial. Okay, so whatever's going on in here, it doesn't really make a difference. It could be going like this. Okay, with all of those little turns and everything, but the end behavior is going to be they're pointed in the same direction because it's an even power, and it's going to be pointing down because that leading coefficient is negative. Same thing here. They're pointing the same direction, so it's an even degree. It's an even power, and then they're pointing up because the leading coefficient is positive. Okay, so what you would do is if you needed to write it out, so you would say, like for this one, right, if they're both pointed down, I'm going to do it like this. Okay, they're both pointed down, so you would write, not AX, but as x approaches infinity, f of x approaches negative infinity. Okay, so as x gets bigger, the f of x, which is the y, goes smaller towards negative infinity. And then here we would say as x approaches negative infinity, f of x is also approaching negative infinity. Okay, that's how you would describe the end behavior for these. Okay. So domain and range, so domain for the x values of these, so the domain is always what are all the possible x values. So here, this x is going to go through everything, right? The x value is going to keep going forever and ever and ever. That's it. Okay, now my range would be really, the absolute maximum is like 2 point something. So that would be my range, is anything less than or equal to that 2 point something, whatever it is, right? So range is all the y values, x is all the, or sorry, domain is all the x values. Okay. All right. Okay, so I can't remember who was asking about the polynomial end behavior, but I think that should answer your question. Okay. So concave down, well, but the thing is that when you, I don't know. concave down, I don't know if we would use that for this polynomial. I mean, I guess you, but the way that you describe the end behavior is more like this, right? But so the big thing to remember is that if it's odd, so sorry, if it's an even degree, so it's like x to the 4th, x to the 6th, x to the 8th. If it's an even degree, they're both pointing the same direction, right? They're either both up or both down. If it's an odd, okay, if it's an odd number or an odd power, they're going to be pointing in opposite directions, okay? So the way that I look at it is that if it's an odd power, okay, if that leading coefficient is positive, okay? So if that leading coefficient is positive, this one's negative. If the leading coefficient is negative, it kind of makes almost like a negative slope, right? So it's going to be up on this side and down on this side. So in this case, these will be like flipped, right? As x approaches negative infinity, f of x is going to be positive infinity. As x approaches positive infinity, f of x is going to be going to negative infinity. So if it's odd, they're pointing in different directions. If it's a negative, it's going to be kind of making a negative slope, right? If you kind of connect those two ends sort of. And then if it's a positive, like this, positive but odd, it's going to be kind of like making a positive slope. Okay. Let me fix this. Lovely, lovely. Okay. An example of the equation for the red line. Sure. So this would be, so this one would be something like, let's see. So the red line, so like I said, I know that it is an even degree, okay? And I know that it's gonna have a whole bunch of terms in there. Okay, so the higher the power, it sort of dictates the more turns that you're going to have, okay? So I know that the leading coefficient is also going to be negative. So something like that would be, so if we did f of x is gonna be, so it's gonna be a negative, so I don't know, let's say negative 4x to the 10th, right? Plus 3x to the 9th minus 2x to the 8th, right? And you could just kind of fill in a whole bunch of these on and on and on and on and on down until you get to like, I don't know, -3, right? Would be your last one. But if you kind of go through all of those different degrees, and you can play around with the coefficients. This is something that's really fun to do on like a graphing calculator or something. It's to just investigate and see what happens, right? See what happens when you play with these different degrees and see if you can spread out these curves, because that will help you learn even more about all of these different things than just like me just kind of telling you what the equation is, but going through and messing around with the, like, what happens if these are all negative coefficients? What happens if they're all positive, right? That's a big part of, especially with these polynomials, is just getting to know them, okay? But yeah, so this one I would say, if you started with a negative coefficient and like start with a power of 10, that'll probably get you enough of an interesting curve in there. Okay. We got time for one more thing, okay? Let's see. Oh, that's my mouse. There we go. Okay, so somebody. Oh, mean absolute deviation and IQR. Yes, Cole, I can definitely do that. Okay. So the mean absolute deviation and IQR are both statistical numbers, right? Statistical values. So they're two different things. So the mean absolute deviation is talking about the distance of your data from the average, okay? Your IQR is talking about the spread from your median. Okay, so your IQR is based off of a box and whisker plot. Okay, where it's kind of divided up your data into 25% into quarters. Okay. So here we go. So it's going to look something like this. Okay. This is 25% of your data falls here, 25% of your data falls here, 25% falls here, 25% falls here. Okay. Your IQR is basically talking about your central 50%. This is your IQR. It's your Q3 minus your Q1. Okay, so whatever value, and this is your median. Okay, so we've got our median here, it's your Q2. So your median is the value that's physically in the middle of all of your data, right? So IQR is a measure of spread, but it's how far spread is it from the middle of your data, right? Because when you're talking about all of these data points, you're really talking about, like, you're concerned about the measures of center. You're concerned about the measures of variation or spread, right? So this is a measure of spread, like how spread out is your data with the maximum and the minimum, and you can use this to figure out outliers and all of that. The mean absolute deviation is talking about your spread from the mean, from the average. So it's sort of like the average of the average. It's the average of how far you are away from your average. For example, okay, if I've got, okay, let's say, this is going to be hard with just a few points, but let's just take a snippet of some data, right? So let's say that part of my data set is 3, 5, 9, and 2. Okay, that's just a snippet. These are the data that I want to find the absolute deviation for. Okay, let's say that my mean is 7. Okay. So what I'm going to do is my absolute deviation is where I'm going to take I've got 3 minus 7, and that's an absolute value. Okay, so that's going to give me 4. Okay, so my absolute deviation is 4 because 3 is 4 places away from 7. Okay. So my 5 would be, I do 5 minus 7, that's going to give me 2. My 9 is also going to give me 2. Oh, that's a curved line. I'm so used to drawing parentheses. So that's going to give me 2. And then 2 minus 7 is going to give me 5. So then what I would do is I would average these together. So I would have 4 plus 2, which is 6, 8, 13, divided by 4, right? That would be my mean absolute deviation. Again, mathematicians are not super creative about what we're doing, right? About what we're talking about. Like the mean absolute deviation, mean is average, absolute value, and deviation is how far away it is from something. Okay, so, oh, the suavemente. I did piecewise functions earlier, so go over to YouTube and you can rewind and rewatch it because I just did piecewise functions. You missed it. All right, guys. So that is about it for me tonight. Of course, I will be back next week. Have a safe and wonderful weekend and week. And if you need any one-on-one tutoring or virtual tutoring or anything like that, click the link and do the stuff, and you can make an appointment and we can work together on stuff. All right, guys, have a good night.
Did you want to do an OBS?
No.
No. You missed all the chat. YouTube.
There wasn't any. It was empty, see?
Oh, there was.
Oh.
You were answering some of them, so I thought it was interesting.
I don't know. Stop